Hi everyone, in this video we're going to be constructing the acceleration diagram for question 1 from your problem set. To do this question you will need to have your velocity diagram for question 1 of the problem set squares, ideally 2, and a ruler. We'll be using pencils, a good eraser, a sharpener, and of course a calculator. So let's get started. From the velocity diagram that we did in the previous video, you need to get your radial acceleration for each of the links. To find the radial acceleration, you'll need to measure the length of the links to get the velocity. So for example, if we were using velocity of d relative to c, I'd measure this length, which is 5 centimeters, convert back using the scale. So I have a velocity value in meters per second. I then use my equation for radial acceleration, which is v squared on r being the length of the links given in the question, and from that I can get acceleration in meters per second squared. So once you have that for each of your links, we can go ahead and start to find the acceleration. This is the same question as before, so we have a crank rotating at 180 RPM in the clockwise direction. The lengths of the links are unchanging, values given in millimeters. We're asked to complete the acceleration diagram and find acceleration of slider D. We also have a starting point given and a suggested scale. From my previous calculations, I know that the radial acceleration of point A relative to O, which was given in the question, can be calculated to be 53.3 meters per second squared. I've then applied the suggested scale and I have a length of 10.6 centimeters. It's important to note with your acceleration diagrams that the total acceleration equals the radial acceleration plus the tangential component of acceleration. In the case of A relative to O, we are told that the link rotates uniformly at 180 RPM. From our velocity diagram, we know the radial acceleration for point A relative to O. Because our link is rotating uniformly, the tangential acceleration, which can be found by alpha, or angular acceleration, times your radial length. If this is rotating uniformly, then alpha equals 0. This means our tangential term for acceleration is 0, and the total acceleration for the link A relative to O can be given by just the radial acceleration. This means we know point A in our diagram. My length is 10.6 centimeters. All that's left to do is draw it in my diagram. Radial acceleration refers to the acceleration towards your center of rotation. So if I have a particle rotating about a center, my radial acceleration points towards that center, and my tangential acceleration is at 90 degrees and causes the rotation. So, in my diagram, I have the link A relative to O. A is rotating about point O, and my radial acceleration points towards the center of rotation. The total acceleration of AO equals the radial acceleration of AO, and the radial acceleration is parallel to this link A relative to O, and it's going to point towards the center of rotation, which is point O. To draw a parallel line, the best way is to put your ruler against the link, set square against the ruler, and a second set square at 90 degrees, which we can slide up and down the previous one to get your parallel line, as you can see. So through the starting point, I'm drawing a line, and I'm going to measure this line to be 10.6 6, as accurate as I can, centimeters. So this is point A, this is acceleration AO, which is equal to my radial acceleration AO. Now we have point A, we can look for the next point in the diagram. So point A is connected to point B. That means we need an equation that defines point B. Acceleration of B equals acceleration of A plus acceleration of B relative to A. B is our unknown. A is known. We just found point A, and we can use the relative acceleration of B relative to A. As we discussed at the start, acceleration has two components. We have the radial acceleration of B relative to a fixed point, the tangential acceleration of B relative to a fixed point. We have radial acceleration of B relative to A, and the tangential acceleration of B relative to A. Remember, we've already drawn in point A. So to find point B, we have to draw 4 lines. Of these 4 lines, we already know 2 of the components. We know the radial components, and that is from our velocity diagram. So if we look at our calculations, we have B relative to A and B relative to a fixed point. We've already used the first one. So back to our diagram, I'm drawing in the radial components of B relative to a fixed point and B relative to A. So to find point B, I'm drawing in 2 lines to start with, and that is the radial component of B relative to the fixed point, and the other one is the radial component of B relative to A. So starting with B relative to my fixed point, radial acceleration points towards the center of rotation, so that will be going upwards towards my fixed point. A parallel line will be ruler along the link, set square along the ruler, and a second set square that will allow me to accurately draw a parallel line. So the radial length of B to the fixed point is going to be 1.8. I'm doing a dashed line so I can tell the difference between my total acceleration and radial and tangential components. This is important when our diagrams get more complicated, as you'll see in questions 2 and 3. So here I can add the direction, and this is a radial component of BP, or BO2 as it's labelled in this question. Now let's do the radial component of B relative to A. B relative to A means A is acting as my centre of rotation. My radial acceleration points towards that centre, so we're going downwards on the mechanism. I put my ruler along the link, set square on the ruler, and then a second set square to get a line parallel to that link. This time I'm starting at point A because A is my centre of rotation. I draw a line downwards, and that length of the line is going to be 1.32. Let me check this length. It's okay. And label it, so our radial BA. So you can see I have 2 of my 4 lines. I have the radial component B relative to P and the radial component of B relative to A. So now to find point B, I'm drawing in the tangential component of acceleration. And as I showed before, the tangential component of acceleration is perpendicular to the radial component or perpendicular to the link in the diagram. So if I draw a perpendicular line, now I don't know the direction and I don't know the length, I just know the location. So this line could easily extend downwards, I'm not sure. Again, I shall do this for my radial component. Now hopefully you can see where this intersection point is. So this line could easily extend the other way, but where they cross, this is point B. I'm going to remove my excess lines, I'm going to draw in my tangential labels. So tangential of BP and tangential of BA going towards point B. Now before we move on, we need to close the triangle. As we discussed, the total acceleration is the radial acceleration plus the tangential component. So if I have my radial component pointing towards the left, my tangential component points up. To close the triangle, my total acceleration will point up. So from my starting point, I can either use the radial component plus the tangential component to get to point B, or I can go from my starting point following the total acceleration line. Once again, point A to point B, I can follow my radial plus the tangential line to get to point B, or I can follow my total acceleration line to get to point B. So once we've found point B, we're going to go ahead, look at our mechanism, and we can see that point B and point C and the fixed point O2, or fixed point P, as it was in the velocity question, are all on the same link. In the velocity question, this meant they had the same angular velocity and we could use a ratio to find point C. For our acceleration diagram, this means they have the same angular acceleration that we can use to find point C, using a similar ratio. So here I'll show you the calculation. We have acceleration of CP on acceleration of BP equals the radius CP on the radius BP. Now we're solving for AC, C relative to P equals acceleration of BP multiplied by the radius of CP on the radius of BP. We know acceleration of BP from our diagram. Now it's important to know that the acceleration in the ratio refers to the total acceleration. So we have to measure the total acceleration line here. So the total acceleration of BP is, I have 8 centimeters, so this will be 8. I'm keeping it as centimeters because I want my value of acceleration CP to be in centimeters so I can measure it straight to the diagram. Our ratio now is taken from the lengths of the links given in the question. I haven't worried about converting these to meters because it's a ratio, so the units cancel each other. This means if I do my calculation, acceleration of CP is going to be 15 centimeters from point P, or from my fixed point. So on this diagram, C relative to P means I'm starting at my fixed point, so that's P or O2, depending on how your question is labelled, and I measure up to 15 centimeters. So this is point C. Write in your total acceleration. Each line has to have an arrow and a label. Now we have point C, we can go ahead and find the next point. So C and D are connected in the mechanism, which means D is the next point I'm looking for. This means I need a new equation. Acceleration of D equals acceleration of C plus acceleration of D relative to C. Just as we've done before, C is my known, D is my unknown point I'm looking for. That's on the left-hand side of the equation. D relative to C has a radial component and tangential component of DC. When it comes to point D, D is a slider here. If you look at the workshop slides, you can see the mechanism in motion. D follows this red dotted line, so it's moving back and forth in the vertical direction. That means it has linear acceleration. It doesn't have radial and tangential components. So I'm going to write linear here. So to find point D, I'm drawing in 3 lines. My linear acceleration, my radial acceleration of DC, which I know from my velocity diagram, and my tangential line D relative to C. Here's my diagram. Let's draw in the radial component of DC first. So I have D relative to point C means my radial acceleration points downwards towards point C, which is acting as the center of rotation. I have my ruler along the link. First set square up here, second set square. Let's make sure this is accurate. And the length this time is very small. It's only about half a centimetre, just over. So radial DC. Even though it's small, it still needs a label and an arrow. Now I'm drawing in my line perpendicular, which is the tangential acceleration. As before, I don't know the length or even the direction, so it could very well extend this way. However, I have one more line to draw in, and that is my linear acceleration of the slider. This will go through the starting point, so that's acting as your stationary reference. I'm drawing a parallel line, parallel to the direction of motion. So again, even with a slider, make sure it's parallel. Don't just visually do a vertical line because it won't be exactly vertical. And where these lines cross, that is point D. I'm going to erase the excess line, write in my tangential component, draw in my total acceleration, acceleration DC, so I can follow my radial plus tangential to get to point D, or you can use the total acceleration. So this is your completed diagram. I'm going to tidy up this label first, as you should in yours, because they get complicated, and if lines cover the labels, then we don't know what's what. So tangential BP. This is your completed diagram. If you had to find the acceleration for any line, you measure that length of the line, remove the scale, and then you'll have a value in meters per second squared. So I hope you found this useful. If you're still confused, please go back and re-watch the workshop, have a look through the workshop slides and try all these questions yourself, and you'll find with repetition, these will become much easier.